All right, so just re-uploaded the slides because I realized I had them a little bit out of order how I wanted to do them today. Kind of starting out, we'll do a little bit of linear regression review. We'll take our first look at some academic papers on Thursday. So I put two up there on Canvas. They're pretty short. And I'll kind of go over them at the end of class, just how you should kind of review those papers before we talk about them Thursday. I'll put up an online quiz after today's class as well. That'll be kind of related to what we talked about today. Should be relatively kind of some simple questions. I think it should be about 3 questions on there. So 7 base points, and then for each one you get correct, kind of building you up to that 10 out of 10 for the day. Also, I will, part of using the dot cam, I just want to mention off the back, is because I realize a lot of people are going to be in and out of class. If you send me an email about like you have to miss class because of you've got a positive COVID test, your roommate, whatever, if I don't respond, I'm trying to respond to all of them. I've gotten a lot. So if I've missed 1 or 2, I apologize. But I am seeing those, because we're not having any in-class kind of points, it's not necessarily that I have to necessarily excuse your absence. And I will try to respond to those as best as I can. Like I said, I'm just getting notifications from the university for individually. So if I do miss one, I apologize. But feel free to reach out to me if that does happen along the semester, and I'll try to kind of keep you as up to date as I can about what we're covering in those courses you miss. Okay. Any questions for me before we kind of jump into things for today? Okay. So, I just started out kind of this slide's linear regression overview. What we're trying to do with linear regression, and this is going to come, into play into this class, we're trying to estimate the relationship between 2 variables, right? So you can kind of think about this in its most simple form is, as some variable X goes up or down, what happens to another variable Y, okay? That's kind of what we'll start out with linear regression. We're trying to estimate this relationship between 2 variables, right? Now, usually we can think of this as it's just a simple linear equation. I might introduce us towards the end of the semester to some nonlinear kind of relationships just based off the papers we're going to look at. But for now, we'll keep everything kind of linear, right? So, if I have just some general equation, right? These variables aren't named right now. I'll put some variable names to this in a second. Y is going to be some function of X, right? If X is 0, A here would be the intercept, right? Where this variable Y starts out if X is at 0, right? Because if, no matter what B is here, anything times 0 is 0. And so A is kind of our starting off point. Right? B is going to represent the slope of some linear equation. We can also think about B as really telling us what's the relationship between X and Y. I'll try to give you a visual of this. Nope, that's not a visual of that. A little slow in the first time we switched this dot cam. So we're thinking about 2 variables, X and Y. What we're really thinking about is something that looks like this. Right? So A is going to be the intercept, or where that value for Y starts out when X is equal to 0. Right? We then can think about the slope is going to represent, let's say X is going from 5 to 6. The slope B represents how much, in this case, the way I've drawn it, we'll call this, think about this as some starting off point. So maybe we'll say 10, that's where Y starts here. The slope represents how much that value for Y is going to change from a 1 unit change in X. Okay. So once we get to the interpretation of this, I think this will make a little more sense, but to kind of give you a visual, this goes back to just a very simple kind of mathematical example where we've got Y as a linear function of X. So that slope will tell us if X goes up by 1 unit, how much does Y change? In this case, the way I've drawn this as a negative slope, so Y is going to go down by whatever that value of B is, right? If I have a downward sloping line here, B is going to be less than 0, right? We're going to have a negative value. Okay? So that's essentially what we're trying to do with linear regression. But what is this line representing? How are we coming up with this relationship between X and Y? We can think about that as we're going to have some data. And if we plotted every single observation in that data set, we're trying to come up with the line that best fits this data. And I won't go in as much depth as you would like in our stats course or something like that, but that's the general idea behind what we're doing. We're essentially, if we really want to be specific, we're minimizing the sum of the squared errors. The errors are going to be how far off our predictions that we're coming up with based off of this best fit line, how far off our predictions are from the actual observations. Okay. So just, if you want a little bit more in depth, if you haven't taken stats in a while, or you feel like your stats class didn't go over that, feel free to kind of stop by my office and go through a little bit more in detail exactly what this line of best fit means. But kind of the broader concept is we're trying to come up with a line that best fits our data. When we find that line is going to have an intercept, and that line is going to have a slope. Okay? Now, mathematically, we can come up with what those values are using regression analysis, right? And using all of our data, right, to find the values for A and B that would give us the intercept and the slope for a line that best fits that data. Okay. And like I said, you can also think about B, or the slope, kind of representing the relationship between that X and Y variable. Okay. Any questions on that before we keep moving? Everyone's taking 221 here, right? Or the math equivalent. It's a prerequisite, so you should have. If you haven't, make sure you come talk to me, and we'll try to figure out, honestly, exactly how you ended up in the class without having it, right? So, that's what we're doing. We'll call, I'll get my slides back up here in class. We'll call Y, or that left-hand side variable, our dependent variable. It depends on the values of X, right? Therefore, we'll call X our independent variable, right? It changes independently of the values of Y. It's what we think is causing Y to change. Okay? So I'll sometimes call, Y, left-hand side, dependent variable, X, right-hand side, independent variable. Okay? That's going to be annoying if it keeps doing this. Let me see if this fixes. There it goes. We're then going to use regression analysis to kind of estimate what that intercept and what that slope for this line of best fit is between our dependent and our independent variable. So, if we had data like this is what I drew. We're trying to come up with what are the values of A and B that would give me a line that best fits this data. In this case, we can see our intercept would be up here. And I already kind of mentioned in the example here, the slope would be negative, right? As X goes up, the values from, based off of our data, the values of Y tend to get lower. Okay. We can kind of think about, maybe we've got something like, the weight of a player and whether or not they, the number of strikeouts they have in a season. Maybe we plot that data and we see kind of a straight line, which would, here the slope would be what? 0, right? There's no relationship between weight and strikeouts. I doubt that's actually true if we look at the actual data, but trying to think about something that maybe might have not a very strong relationship. It's likely it'll never be completely flat, but it will be, pretty flat. We could also think about, I think here what I do, goals scored in the previous year and the salary the following year, right? You can probably imagine as someone scores more goals, whether this is, NHL, however you want to think about this, you can think about this as touchdowns, whatever sport you want to think about, right? It's likely that the salary is increasing. So if we were to estimate this line of best fit, right, the value for our slope of B here would be positive, right? And then I kind of had another negative relationship. All right, we think about maybe weight and stolen bases. It's likely we expect a negative relationship between those two things. As someone is a higher weight, we expect that they see, as the weight of a player goes up, the number of stolen bases we see they get, goes down. Okay. We can write this a little bit differently, and this is typically how we'll see this in the papers that we look at. But instead of A and B to represent our slope and our intercept, we kind of see them write it as beta 0 being the intercept, and then beta 1, right, being our slope for the relationship between X and Y. Okay? So a lot of times we'll see the slope and the intercept kind of referenced as beta as opposed to A and B, how we might have seen it in other courses or kind of more typical math class, sorry, I should say. So the general form of the interpretation, whenever we look at the actual output from regression analysis, once we actually come up with a value for beta 0 and beta 1, beta 1 can always be interpreted as the expected or the predicted change in our y variable from a 1 unit change in our x variable. Now, those units will depend on the variables we're using, right? If I'm using weight, a 1 unit change is 1 pound or 1 kilogram, right? If I look at age, it'd be 1 additional year of age, right? So the units will just depend on the type of example we're looking at. And then beta 0 can always be interpreted as this is the expected or predicted value for our y variable if that x variable is equal to 0, right? Now, the interpretation on this intercept will sometimes make no sense. If we just want to think about the relationship between weight and stolen bases, then if we came up with a value for beta 0, there it would be, that's the predicted or expected number of stolen bases if somebody weighed 0 pounds. I mean, that doesn't, we're never going to see that in the data. But the reason why is because, let's think about, we'll keep running with this weight and stolen bases example. So let's say I've got weight down here and stolen bases as my y variable. It's likely, right, that the data looks something like this, because nobody is weighing less than, I don't know, I'll choose a weight here, maybe someone does, but it's unlikely we see a lot of Major League Baseball players weighing less than 150 pounds, right? So all of our data is going to be over here. So when we come up with that line of best fit, it's still going to have an intercept, right? Think about this as beta 0 maybe, but it's just that we're never going to actually see a data point that's over here at the intercept, but that's still how we interpret the intercept. Okay? Is that making sense? Any questions on that? Okay, so those are kind of general form of the interpretation, no matter what the variables are. So maybe we think about how is a basketball player's salary impacted by the number of points they scored in the previous year. Right? So if that's the relationship we're trying to estimate, we think that the salary depends on the number of points scored in the previous year. Then our regression equation, what would our dependent variable be? Yeah. So if our dependent variable or our y variable is the score from the previous year, exactly, right? Our dependent or our y variable is what we think is going to be changed by the points scored. So it's salary. Yep. And then what do we think the independent variable is? Number of points scored in the previous year. Exactly, right? Now, if we were to write out this regression equation, it's going to look something like this, right? We've got our salary, which depends on the points scored, and we're trying to come up with a value for what that slope coefficient is, right? Or what represents kind of the correlation between points scored in the previous year and the player's salary the following year. Okay. And then beta 0 would be our intercept. It's, to be honest, we're not really going to ever focus on the intercept. I'm just trying to kind of give a little bit more of a background and a kind of complete review here. Okay. So we run this regression analysis, which we're not going to do by hand. Anytime we do that in this class, or what would be expected of you on your project, would be that you do this in Microsoft Excel or a more, I guess, complex program. So Stata, SAS. So I guess if you know how to program in R, you could use that. But there's usually built-in tools so that we don't have to do all of this by hand. Right? If I took the time today to review how we do it by hand, you would, we'd be reminded this would take forever if we've got a couple thousand observations. Okay? So there are going to be some constant values that Excel is going to spit out at us, or some other computer program. Okay? But once we have them, we can use them to make predictions and to make interpretations. So for example, and here I just reiterated the kind of general form of the interpretation of our slope coefficient beta 1. But let's say, I'm trying to estimate this relationship between points scored and salary. And I run this regression analysis in Excel, and it spits out, these are the values for your intercept and your slope that would give you the line of best fit. Okay. So right away, looks like the number of points scored in the previous year and a player's salary the following year. What type of relationship exists between those? Yeah, positive relationship, right? We came up with a positive value for that slope. So this is telling us as the number of points scored in the previous year goes up, the expected player's salary, the predicted player's salary the following year will be higher. Exactly how much higher? Well, what's a 1 unit change in our x variable? Our x variable is the number of points scored. So for every one additional point scored, the salary of that player increases by about $4.23. Now, this might seem small, but if you think about it, I mean, in a lot of sports, 1 point in a season isn't that many more points scored, right? So sometimes this effect will be very small, right? Because our units are small, right? But if we're looking at a sport like basketball, I mean, you could talk about a couple hundred additional points scored in a year, and that's not that significant of an increase, right? If you're talking about over the entire season. So even though we can get the effect of 1 unit, right? And then, we want to think about how we can make predictions for salary. I could say something like, okay, what if somebody scored, I don't know, 500 points the previous year? What would their expected or predicted salary be? All you would have to do is plug in that 500 points into your equation, and it'll spit out at you. Well, I guess spit out, like you got to put it in your calculator, right? And it will give you the expected or predicted salary for a player who scores 500 points. Okay. So all I would do there to come up with different predicted salaries is plug in different values, that I would want to predict the salary for the number of points scored in a year. I can also do things like, if I know the effect of 1 additional point scored in a year, how could I find the effect of an additional 100 points scored in a year? I would just take that slope coefficient of 4.23 and I would multiply it by 100, however many unit increases I'm interested in. It's always going to give me the effect of 1 unit, but I can find the effect of any number of units by simply just multiplying that by my desired increase in points scored here, or whatever the desired increase in whatever the x variable is. Okay. So we'll see this used a lot in the papers that we look at. We kind of already interpreted this. And then, of course, the intercept would be if a player scored 0 points in a season, we would expect their salary to be what, $250,000. So this would be like someone's on the bench who never plays. We would still expect them to have a salary of probably, the league minimum or whatever it happens to be, right? And whatever league we're looking at. Okay. Is this making sense? Are there any questions on this up to this point? Okay. So let me see if so what's one problem, right? With running a linear regression, a very simple linear regression like this? What's probably true about, let's say we're not looking at basketball. Let's say we're looking at, I don't know, football, right?
I'd say the values are probably look more like a quadratic because the more star players would be paid a lot more than what like a linear progression would be.
Yeah, so you're thinking way further than I am, which is definitely true. It may not be a linear relationship, right? It could be a quadratic relationship. We could have an exponential relationship. We won't touch on that, like I said, until much later in the semester. I might introduce the idea of quadratics, right? But you're right. We might want to try to fit a nonlinear relationship. But let's just assume for a second it is linear. What's something else that's going to be a problem with this?
I was gonna say injuries and stuff like that. Like for a star player to get injured, he is getting paid a lot, but he didn't get that much points.
Yeah, right. So what you're saying is it's not just the number of points scored that matters, right? There's a lot of other factors that I'm not accounting for here, right? Not only getting injured, but let's think about a sport like football. Points scored only matters for half the team. Well, it matters for the defense as well, but I'm unlikely to see near as many points scored by a defensive player as I am an offensive player. So there's probably a lot of other things that I want to account for here, right? So how can I do that? I can use multiple linear regression. And all multiple linear regression means is I include several other variables there on the right-hand side. So I'm still trying to predict salary here, my y variable, but now I know that it doesn't just depend on the points scored. And I think I was thinking about the NBA in this example, but you know what? The number of assists, maybe I've got data that has WNBA and NBA data. I know there's a significant difference in salary between the two leagues. So maybe I want to include an identifier for like, is this a male or female player, right? Or do they come from the NBA or WNBA? Or there's a lot, and I put 2 in here. There's probably 30 other variables I'd like to throw in there on the right-hand side that I think would be helpful in predicting salary. Okay. So Excel can still do this for us, right? It can, and it's hard to visualize this. I could give you a nice visual when we had one variable of that simple like line of best fit. Basically, when you have multiple variables on that right-hand side, we're going to get this line of best fit that we can't visualize. I mean, maybe if it was 3-dimensional, it's like it best fits this 3-dimensional, plotting of the data. once we get more than 3 observations, it's really hard to visualize, but it's still, in essence, giving us a line of best fit just on a dimension that we can't even visualize. All right, so it's really powerful. And once we're able to do this, we make a small change to the interpretation of the slope coefficients there. And that's just kind of another name for the slope, right? The slope coefficient is like an estimate for what that slope is between our X and Y variable. And I'll kind of use that terminology quite a bit. It's slope. I'll say slope sometimes. I often slope coefficient, right? It's the estimate for what that slope is. Excuse me. So the thing that we add to our interpretation now, so let's say we still want to interpret beta 1 or our slope between points scored the previous year and salary. It's still the effect of 1 additional point scored in the previous year on the expected or predicted amount of the salary. But we add in this other phrase, which is now holding everything else on that right-hand side constant. So it's just a small change, but I mean, think about how powerful it is. Let's say I had a bunch of other variables that I couldn't fit up on the screen here. You know, maybe I control for their height, their weight, number of years in the league. Now, what I'm saying is, if a player scores 1 additional point, this is the predicted change in their salary, holding constant the number of assists, the number of rebounds, their height, their age, number of years in the league, all these other things. So the thought experiment that we can do with our regression analysis output is 2 players with the same number of assists in the previous year, same height, same weight, same age, same number of years in the league, same position. We could even add in indicators for what team they were on, but one of them scores an additional point. That's the expected change or increase, or I shouldn't say increase here. It was in our example, but right, the expected change in their predicted salary. So that's a lot more powerful, right? So you can kind of envision, and you know, if you've taken some additional stats courses, there are some issues with what I'm about to say, but for the most part, we like to try to throw quite a few variables there on the right-hand side if we think they matter in predicting that Y variable. There starts to become some issues if we don't have enough observations. We can something called over-identification, but for the most part, and for the sake of this class, we want to try to get as much data and control for as many other things as we can on the right-hand side there. Okay. Is there anything else I want to say here? There is, but it's not in the slides. So let's think about a little bit more review of some kind of statistics stuff. So we'll step away from linear regression for a second, and then I'll quickly come back to it. But I want to kind of give you something that you might be more likely to remember from ECON 221 or whatever your stats course was, which is, let's say that I've got some, mean, and this could be for any variable. So maybe we think about height, right? So maybe the average height in a given league is, I don't know, let me think what would make sense. Not 70, probably something like 74 inches or something like that. If I just take any random 10 players and I find the average height from that sample, well, yeah, the most likely outcomes are going to be the values right around 74, right? So if I think about here, if my y-axis was probability, the probability of the values really close to the true overall mean will be the values that are most likely for me to see when I take a sample of 10 players. But it's very unlikely, right, that if I took 10 random players, I'm going to see the average height be 7'2", or the average height is going to be, I don't know, 5'2", right? So values further from that overall true mean, right, are going to be less likely for me to see from my sample, while values, right around that population mean are more likely for me to see from that sample mean. Okay? So this is the idea that if I only have sample data, I usually can't see this, right? But I know that I'm more likely to see values from my sample that are around whatever that now, they may be a little off, right? I might take a sample and I see a sample mean here, which is a little bit off, right? But I can guarantee that that sample mean is going to be closer to whatever the true mean is from the entire population that maybe I don't have data on, right? If I have a really, really high sample, right? Because as I take a higher and higher sample, what ends up happening is the distribution starts to get a lower variance or become kind of a much more narrow distribution or a higher distribution, however we want to kind of, whatever adjective we want to assign to that. Okay? Now, like I said, I'm not going to go completely into review that, but that's the general idea. Whenever we have a sample statistic, if we can get a higher sample size, we can kind of guarantee that if we're only taking one sample, it's much more likely it's going to be very close to whatever the true population parameter would be. The same thing applies to linear regression, right? So if we're thinking about when we're coming up with these values for the slopes, let me think about here, right? There's some true value for that slope coefficient. Like if I had all the population data, there would be some true value for that slope. I'm only seeing estimates, right? Based off the sample data that I have that I've run this regression analysis for. So we're still going to have a distribution. That is a little off, but you get it, right? There's still going to be a distribution that's centered around whatever that true relationship is. And I can guarantee that my data is, the sample slope I see is going to be closer to the true population slope if I can take a higher and higher sample size. So in addition to that, let's say I think about my previous example and I saw that 4.23 as the estimate from my regression analysis for that slope between points scored in the previous year and salary. Well, if I see 4.23, maybe the true relationship is actually 0. That doesn't make sense in the context of what we're doing, but stay with me for a second. And we saw a sample estimate for that slope of 4.23. Now, it could be that the true relationship still is 0, and we just happen to see something kind of close to it, right? That still had a fairly likely, probability of us seeing that. So how do we know if the estimate we're seeing actually is any different from 0? Well, we know things about the distribution of sample statistics. And if, in fact, the true relationship was 0, there's going to be a certain point at which it becomes so unlikely that we see, let's say a value of 10.3, that we're okay saying, look, I saw something way out here. The probability of seeing that value, if in fact the true relationship was 0, it's so unlikely from my sample I would see this 10.3 as my estimate that I'm okay saying the relationship can't be 0. It's probably more likely that the distribution of these sample slopes is probably centered around the true slope, which is, maybe in the way I've drawn it, maybe something closer to 8 or something closer to 10.3. So at what point am I okay rejecting that the relationship is 0? And what we're going to do, we could do a whole review of what p-values represent, but honestly, for the sake of this class, what's probably easier is just to kind of remember the rule, right? So we have this thing called a hypothesis test, which is we always start out assuming that our slope is equal to 0. We're going to try to use our data to see, is that actual relationship between X and Y anything different from that? And we're okay, what we'll say is we're okay rejecting the relationship of 0, which, makes sense in a lot of times what we're trying to do, right? Like if I wanted to know, does the salary depend on the number of points a player scored the previous year? I'll start out saying, no, it doesn't. And if I can find evidence that goes against that, I'm okay rejecting that assumption. So when can I reject that assumption? It's anytime my p-value is less than this thing we call alpha. And alpha is essentially something we'll set that we say, look, this is the threshold that we're okay with. If we see, if the probability of what we see is 0.1, then we don't want to reject this. But if it's anything less than that, right? If the probability is any less than 0.1, or the likelihood we saw the sample estimate we did is anything less than 10%, essentially, right? Probability of 0.1, 10%, then we're okay rejecting. So the 3 threshold levels that are kind of standard is, I don't know if I can talk right at the same time, 0.1, 0.05, and 0.01, right? And these would kind of correspond to saying I can reject that there's no relationship between those two variables, or said differently, I found that there is a significant relationship between those two variables with 90% confidence, 95% confidence, or 99% confidence. Now, obviously, always saying it with a higher level of confidence is great, but sometimes we don't have a p-value, or the probability of seeing the sample statistic we did doesn't become as low as 0.01. So sometimes we can reject with 90% confidence that there's no relationship. Sometimes we can reject with 99, right? And the way that we'll typically see this in the papers, and I'll review this again once we actually look at them, is we're kind of notating this with stars. So anytime I come up with an estimate for what that slope is, it may differ from 0, but I can only statistically say that it's different from 0 if the p-value falls below these different thresholds, right? Because let's say, I saw this was 4.23. Okay, it looks like it's different from 0, but if the p-value, or the probability that I saw that sample estimate, let's say it was, I don't know, 0.8. Well, if there's an 80% chance of me seeing this value, if in fact the true relationship didn't exist, well then, it's still very likely that there is no relationship. I just happen to have a sample that was a little bit kind of to the left or the right of that true relationship of 0. So in this case, right, 0.8 is not less than any of those thresholds. So I would fail to reject that there's no relationship. Well, that happens sometimes. It's okay. It's just, I didn't, the data told me there's no relationship with these two variables. That would make sense if I had something like, I don't know, salary and, I don't know, players' eye color or something like that, right? So sometimes there just is no relationship between two variables. But if I ever come up with a p-value, I don't know, let's say it's 0.07. What that's telling me is that the estimate that I found from my regression analysis, I'm okay saying that there is a relationship, right? Because I can reject that there's no relationship at the 90% level. 0.07 is less than 0.1, so I can reject that there's no relationship. Or said differently, I found strong evidence there is a relationship. At least I can say that with 90% confidence. However, I couldn't say that there's a relationship with 95% confidence because 0.07 is not quite less than 0.05. Some of this ringing a bell? Hopefully. A couple of you I know hasn't been too long since you had stats. So, like I said, once we start going through papers, I'll remind us of these things over and over again. I'm just trying to kind of set us up because we will start looking at papers for support of the theory that we look at. We'll start discussing them kind of at the end of every week. And I want to make sure that kind of going into it, we're at least kind of a refresher of some of the terms and kind of overall what we're doing when we look at this regression output. Okay. So we're mainly going to focus on the value of the coefficients, but also kind of whether or not they're statistically significant, whether or not we can reject this null hypothesis, there is no relationship at these kind of 3 different benchmark or threshold levels that we typically look at. Okay. All right. Any questions? We kind of keep moving. We'll kind of transition away from linear regression. I just want to give a little review today. Then we'll look at that paper Thursday. So we'll get a little more kind of refresher of it on Thursday as well, kind of a little bit in each class. Okay. Okay with that? For now, at least. All right. So let's get to some more interesting stuff, I think, for today. So we'll kind of go through this a little bit quickly so we can look at some actual data. But one thing that we need to think about is a lot of the examples we're going to look at, and I think I mentioned this last week, are going to be a little bit different than our typical goods, right? So we think about the output and the kind of production function of a lot of these different examples. Let's think about just a handful. So some will be sport related, some won't be. So if I'm thinking about Ford Motor Company, what's their output? Vehicles, right? Cars, trucks, whatever specific automobile we're looking at there. Right? And I think I actually, what about Facebook? This is kind of a weird one. What would their output be? Probably users, like number of users or the amount of user data they're able to collect, right? Because that's ultimately the product they sell to other companies. It's weird because you would, and I guess no one really uses Facebook probably anymore, but right, the idea is these social media companies, right? They're trying to get users, right? So they can sell the number of users data or to different companies, ad companies, things like that. Why is this not? There you go. What about Ball State? What's their output? It's kind of weird, but yeah, like probably completed degrees, right? That would be a nice measure of kind of their output, right? How many graduates they're kind of putting out there in the world. Now they may also have some output, which is like research, right? From professors, things like that. What about Alabama football? Their output is so maybe it's their players, right? But probably where is most of their money coming from? It's actually just playing the games, right? I mean, obviously, like for them, NFL prospects are a byproduct of their ultimate goal, which is to have a high quality program so that they can sell tickets, sell ads, right? So really their output might be the number of games they're playing, but also might be kind of the quality of their games, right? So we're going to have kind of a little bit ill-defined kind of terms in what the output is, right? It's kind of hard to measure, right? But we have metrics we can use like wins, right? That kind of tells us the quality of the team, maybe championships won, something like that. So the output market's going to be a little bit different when we look at some of these sports examples, right? It's not going to be necessarily as much of a physical product as it is, the number of games being played, the number of ads kind of that they're able to kind of produce. So, it'll change depending on the context of what we're looking at, right? So we should think about all four of these, and I try to choose ones where really the output is significantly different, right? The very first one was kind of a traditional product we think of, like a physical product. But the other three, you can see it kind of can become abstract. Not abstract, but it's just not as straightforward as you would kind of think about the products we probably were talking about in 201. So what is their production function going to be? If we think about Ford Motor Company, their output is a function of the capital and the labor, right? It's typically how we think about it. But if we're thinking about kind of output as the number of wins per season, right? We're thinking about the quality of the team being kind of the output. We're using wins to measure it. Well, then instead of Q being the quantity of the product, sometimes we'll just start writing in W here, just to make it a little bit easier, right? It's still the product, right? The quantity of what they're producing, but we're measuring it, like the actual data that we're measuring this quality of the team with is the number of wins, okay? So wins are their output. What are some things that might influence this? What are my inputs? What's the main input? Players, right? So I could break this down into a bunch of different components. So maybe I don't just think of this as quality of my players. I break this down to the quality of my offense, the quality of my defense, right? And I think that's how I'll write it here on the next couple slides. So maybe the offensive talent and the defensive talent. So just kind of talent here, denoting it with offense and defense with a subscript. But if I really want to be more precise, I would actually break this down by every single position, right? The talent that I have at quarterback, the talent I have at running back, the talent I have at offensive guard, the talent I have at kicker, right? I mean, I'll go through the list. What are some other talents I could actually add in there? Not just my players, but maybe coaches get in there, right? So there's going to be a lot of different factors that my wins are going to be a function of, right? So I come up with a production function for the number of wins by kind of thinking about all the different inputs that I have. And, we'll never be completely exhaustive, like probably especially in the way I write this out, because there'll just be too many things to add in there. But that's what the team is thinking, right? You've got talent at every position. You've got coaching talent. You might even have facilities. Maybe think about that. It's more of like a capital, right? I've got some facilities that will add to the performance of my team, right? I've got better, weight training staff or physical trainers, things like that, right? So, we can write this in a very simplistic form, which is that wins are a function of different types of talent. I kept two here just to keep it simple for right now, but like I said, you could expand this quite a bit. Right? So what's my kind of marginal production, right? So if the talent rises, right, I'm going to increase the number of units of talent I have at different positions. Here, just kind of thinking about it, simple offense, defense. I might see an increase from that increase in talent in the number of wins I have. Right? Oops. So the way I'll write this, and we can kind of use, I'll just use kind of a triangle here to denote change. I'll shorthand the word change a lot, especially when we're thinking about marginal effects of things, as the marginal production of my offense is the change in the number of wins that comes from a change in the number of units of talent. Right? Now it's going to be hard, we'll go into lengthier discussions and we'll see the way that some researchers have tried to estimate what a unit of talent is. But for now, just think about, it's a little bit abstract, but think about just upgrading to the next best player. If that's the easiest way to think about it, right? What would the change in the number of wins be from increasing to the next best player at that position, or the next, adding the next best offensive player to your team? Or here we have the marginal production of defense being the change in the number of wins and the change in the units of talent on my defense. Okay. So this thing about this is usually we have something like the change in quantity from like a change in the number of workers I have, something like marginal production of my labor. Here it's just labor is a little bit more abstract because it's not just adding another player, it's adding a more talented player, right? How does that change my output or my production of the number of wins, the quality of my team? Okay. So if I had the marginal productivity of my offensive talent and the marginal productivity of my defensive talent, right? We can kind of think about initially, let's say we start with 0 players. When I add that first, what player am I going to add to my team first? It's going to be the player who adds the highest number of wins. Right? So maybe if I think about football, I guess if you have a little bit of knowledge, probably you would think about maybe I want to add, there's probably people who would argue this, but maybe I want to add the best quarterback that's out there. Right? I think that adding this quarterback, initially, he would increase the number of wins my team has by 2. Problem is, then who do I add next? Well, I'll go to the next most efficient position. And that, you could argue what that is. I don't know without looking at the data. Maybe I'll add an offensive lineman or maybe I add a running back, right? But as I add players, what happens? What's probably the last player I think about adding to my team if I'm starting from scratch? We'll pick on some positions here. Maybe a kicker or a punter, right? And that's because I think that they don't add near as many wins to my team as maybe these other positions did, right? And so essentially what that's telling us is we have a law of diminishing returns, right? As I add talent, that talent adds a smaller and smaller number of wins, right? And also I should say here, when we're talking about adding a number of wins, this is always the expected number, right? Because every team is doing this. Someone has to win, someone has to lose. So this is going to be the expected number of wins. Once it's realized, like even if I predicted that based off the talent I acquired, my predicted number of wins would be 10 games. Well, potentially, right, there's a distribution on like performance in every direction. So maybe I don't quite meet that expectation, but ahead of time, I'm building for the expected number of wins. Okay? And I may not always say expected, but that is in practice more we should be thinking about. So I've got this law of diminishing returns, which is going to say, as I add more and more talent, it's going to add a smaller and smaller number of additional wins. And this also makes sense in the context we'll use football because I think it's maybe we can visualize a little better. If I win 15 games in a season, I mean, as I'm adding additional talent, there's not as much room to grow once I start to get a higher number of wins. So just the nature of having a finite number of games is going to make this so that the marginal productivity is diminishing as well. Now, what's something that happens with labor, right? It's not always diminishing, right? So just remember the term for like initially, as I'm adding talent, I might actually not see my marginal productivity of talent decrease. It potentially could increase initially. So the idea there would be, if I add some talent at quarterback, well then, if the next unit of talent I add is that offensive line, they can protect my quarterback. My quarterback in turn becomes more productive. They're kind of complementary. Remember what the term for initially we might see marginal productivity increasing as a result of.
Is that economies of scale?
So not quite. So economies of scale would be as I increase output initially, you could think about it at some point could be increasing, but more specifically in terms of my inputs here, that's as I increase my production. But you're thinking about along the right idea. Here, think about this as I add in generally more labor, what initially might occur is I can allow my labor to specialize, right? So as I add more players, right, there might be some specialization initially, right? so that, if I had one player, let's think about the craziest example, they got to play all 11 positions. They're not going to add very many wins to my team at all. But as I add more and more players, right now I have a full team. Now each player becomes like more efficient. So adding kind of more talent there initially might see some specialization.
Wouldn't that be the Giffen? Like,
So you're thinking of a Giffen good, which is more related to the price of the good, right? But here we're just specifically thinking about output or production. Yep. Okay. But for the most part, right, we're only going to really be concerned with a portion of adding talent where it starts to diminish, right? Because if it's increasing, like we'll always continue to add talent there, right? Because eventually it's going to become a discussion, right? Adding more and more talent to my roster almost, is almost always positive. Like I said, it could be zero. Where would the marginal productivity of adding talent start to become zero? Or how would that occur?
Start adding backups.
If I start adding backups that never play, right? Now, if I add a backup that potentially could play and a lot of injuries, they're still going to add a small, minimal, right, expected kind of number of wins. But at some point, I'm adding people to the practice squad who never enter, never make it into the game, right? And there we could see it be equal to zero, right? It's very unlikely that this ever becomes negative. Although, so we think about, you're at every single position. Maybe an easier way to think about this diminishing talent is not across the entire team, but just think about one position. So at quarterback, when I add that first starting quarterback, they're going to add a high number of additional wins to my team. Well, then I get another quarterback, add more talent to that position, but they're a backup. They don't really ever hardly make it into the game, barring injury or some, rare patch. So their marginal productivity is going to be much lower than my starter, right? So within position might be an easier way to think about this law of diminishing returns. Okay. I don't know what I think. Yeah, I already kind of went through this. We add offensive linemen. So here, we're thinking about adding things like backup. When I say the number of wins, it doesn't have to be an integer value. It could be that they're adding a fraction of a win, right? And then if I add up those fractions of a win across my entire team, right, then I'm starting to get numbers that make more sense, which is like an expected number of wins of 8, 9, 10, something like that. So we might be thinking about marginal productivity. It's not necessarily going to be that they're adding an entire win. It could be like 0.05 even. Excuse me, right? So it could be a really low number, and that's just because we have so many players in the team. The additional wins each player adds, we will then add all those up to get our expected number of wins. Okay. Now, I've thought about, I don't know if this is the case, but let's think about quarterbacks and backup quarterbacks. Can you think of a scenario where maybe marginal productivity becomes negative? If I have let's say, who do I want to use? Who played last night? Let's say I have Matthew Stafford on my team, right? Pretty good quarterback. And then I say, okay, I'm actually going to, somehow I have enough money. I don't know if, this may not be the most realistic scenario, but I have enough money. I'm going to also add Kyler Murray to my team. Why am I adding Kyler Murray to my team? Definitely talent, right? So I'm seeing an increase in offensive talent. Why might the number of wins I see actually go down? What could happen if I had that scenario? Yeah. Potentially less money to pay for other positions, right? Or what's another scenario that could even happen, even if I had enough money?
I was going to say, you're going to be fine for positions. So like the first person, say Matthew Stafford wins, they say he performs poorly, like the first couple games, and they're going to switch out. And then
yeah, I could have a quarterback controversy, right, where it disrupts the kind of team cohesion, or however you want to kind of measure that. And we've seen that happen. So I think I had here, it's an old, maybe I didn't. Yeah, so I had an old one, right? The Tim Tebow effect. So this has been so long ago now that I probably should find a better example, but maybe I'm stuck back from what I remember. So when he went to the Jets, like, it was this big thing. Actually, we could use it for last year when he went to the Jaguars, so apparently to play tight end, right? It was this big media thing, right? Potentially detracts from the team's performance, right? Now, we won't often be concerned with that because we don't have, it's in the most frequent scenario. But for me to say that it's always going to be greater than or equal to zero, I think you could argue that's not technically correct, but we'll kind of base the assumption that we're not going to be adding any player that's going to kind of cause those types of controversies. Yeah.
Like another example, maybe where that scenario could actually increase the number of wins. It's like say for example, there are two teams that could have equally as good quarterbacks.
Mhm.
But instead of just like having just some throwaway extra, you could have probably picked that second quarterback that was good, just to limit the options for the other teams.
For sure. Yeah. So I'm not saying backups will always be negative or always be zero, because you're right. The reason why we expect them to be greater than or equal to zero is because often adding a backup, right, you could be taking talent away from another team, right? Would complicate our model quite a bit, but you're right. In practice, that would be another component as well. Yep. All right. So marginal cost, right? So we talked about marginal production, or kind of the additional output coming from additional inputs. We can also think about, well, yeah, I would love to just continue to add talent over and over, but at some point, I have to make sure I have enough money, right? So eventually, we're going to be kind of comparing the marginal production of a player to the marginal costs, right? So marginal costs, we can think about it's the additional costs that come from producing an additional unit of output. Well, if our output is wins, right? Our wins, right? To get an additional win, we're going to have to increase the amount of money we spend on talent, right? So, So we're kind of thinking about this as it's the additional cost that comes from an additional win, right? Or if I want to get one more win, what's that going to cost me, right? What's the change in my cost to get an additional win? So kind of think about it this way. In general, when we have our supply curve, we have these marginal costs, right, that are increasing. The same thing is going to be true here. As I kind of increase the number of wins, right? So think about if I want to go from 1 to 2 wins, what's the change in costs or change in my expenditures that are likely going to occur in going from 1 to 2 wins, as opposed to going from an NFL 15 to 16. Right? Well, going from 1 to 2 wins, right, isn't near as difficult, right? I might not have to spend near as much money as, once I'm at 15, I'm already so good. I'm going to have to spend quite a bit more money to get to that 16th win. So we can kind of think about there's this inverse relationship, right? So as I kind of continue to increase the number of wins, that marginal cost is going to become, I said it's inverse. Oh, it's not an inverse relationship. I'm jumping the gun. So as I want to increase my number of wins higher and higher, I'm going to have to increase my costs more and more, right? So the same one win is going to cost me more money if I want to go from 15 to 16 wins as opposed to 1 to 2. So I've got increasing marginal costs, but those marginal costs will also be inversely related to the talent that I need to add, right? So when I want to go from 1 to 2 wins, I probably don't need to increase my talent level near as much as if I want to go from 15 to 16, right? It's just a much harder jump to make. And this is, let's see if I have it. Yeah. So this is, kind of falls in line with our traditional kind of labor models, or kind of our traditional product markets you would have learned in 201, which is the idea that as I want to produce more and more, it's going to require a higher number of workers as my output increases, right? And if workers all kind of cost the same, then, to get that 1,000th unit, it's going to cost me a lot more because I'm going to have to hire a lot more workers because they're not near as efficient as when I wanted to produce that first unit. I just had to hire the most efficient worker out there and only pay one worker. Same idea kind of here. Initially, to get one additional win, I may only have to pay, I only have to hire 1 unit of talent, right? However that looks, it doesn't matter position or sport or anything. To get one more additional win, maybe I only need 1 additional unit of talent. But eventually, right, as I start to see, win a higher and higher number of games, now to get 1 additional win after I've won 15 games, right, I'm going to have to hire a much higher number of additional units of talent. So maybe instead of 1 unit of talent, to go from 15 to 16 wins, I need 10 additional units. Well, if every unit of talent costs me the same amount, this is where, we're not necessarily thinking about the number of players here, but like the amount of talent, units of talent, then, as I want to win a higher number of games, I need a higher number of units of talent, which is going to cost me money or increase my marginal cost to that 1 additional win as well. So these two things are kind of inversely related. We're on time. So I think, let me see where we're at. Okay. I might save this till next class. I might jump around a little bit. We'll jump around a little bit. We'll come back and we'll think about we'll kind of think about monopolies and the ticket market next class. But I've got some interesting stuff down here that I just wanted to take a look at. Okay. So a couple, I went out and grabbed a little bit of data. And I think it's just more interesting to kind of look at, kind of setting us up for next class. Next class, we'll kind of think about this idea of production. We'll go into, okay, so if I want to win additional games, so I'm going to increase my output, I'm going to have to increase my costs, but I also can think about, as I increase the number of games I win, I'm likely increasing my revenues as well. So what's the optimal number of games that I want to choose, like kind of target, expected number of wins to maximize the difference between revenues and costs, which would represent maximizing profits, right? Difference between revenues and costs being my profits there. Total revenues, total costs. So if we look at kind of some of the data out there, as you would expect, if a team has a higher kind of revenue stream, we expect that they're probably going to have more money to spend on talent, and they're going to be able to target a higher number of additional wins. Now we'll see how this plays out graphically next class, but I want to kind of foreshadow it with some data. Okay. So here, I believe this was Major League Baseball I went out and looked at, specifically because there's no cap, right? The other leagues, there's some caps, so I have some additional issues that we haven't, we'll dive into later. But here, and I think this is this would probably be in billions, I guess. I'll pull up the Excel file here in a second. But right, as I see the revenue of a team increase, I also see kind of the wins increase as well. I kind of had a line of best fit through this data. Okay. Now, it's pretty noisy, right? There are some teams that are spending, or making quite a bit more money than others, and they still aren't seeing a high number of wins. But this is just a snapshot, right? This isn't any one year. If I probably wanted to really get the true relationship between revenues and wins, I probably want to do something like look over a 10-year period or something like that. Because, right, there are ebbs and flows to every team in terms of restructuring contracts, things like that. But in general, right, even if I just take a one-year snapshot, I can kind of see the line of best fit between revenues and the number of wins looks like it's positive. Okay. And I can think about, if my revenues are higher, why might I see a high number of wins? This is because I can spend more money. So maybe we'll take a look at the relationship between costs, right? And this is primarily player salaries, right? If I look at salary expenses, and I think this was it's kind of in millions, like maybe I think this was average per player, and the number of wins, Major League Baseball once again, so we've got kind of up to 162 games. And you can see there's also a kind of slight positive relationship there as well, which makes sense, right? As I'm spending more money on players, that should translate to acquiring a higher number of additional units of talent. So as I acquire more and more talent, I should see the number of additional wins also increasing, right? We have the marginal productivity of offensive or defensive talent in baseball. That's not quite what we were saying, right? You could probably combine, one player is producing both of those things in Major League Baseball, but it's the same idea. Even if the inputs change a little bit, the change in the number of units of talent should increase the number of wins, or at the very least, it would be zero, right? And we can see here, as they're spending more and more on their players, which would translate to acquiring higher and higher number of units of additional talent, we see the relationship between that and the number of wins is also slightly positive. Okay. So this is just based off of some data. Also, just to kind of put into context some of the stuff we're going to be looking at, Forbes does a pretty good job, and I've got some links here I'll show you. And they used to only put out the top 5 kind of highest valued franchises, and in more recent years, they've put out entire lists. So one thing that we'll kind of look at here is across these 4 main leagues, and we can look at other sports as well, but primarily for American sports, right? These are kind of the 4 by far and away largest leagues that we have. So NFL, Major League Baseball, NBA, and NHL. Right? Now the NHL is a little bit different because we've got kind of more of a Canadian presence. But if I'm looking at just this in 2016, what league looks like it probably has the highest demand? If I'm using team valuations as any evidence of consumer interest, so these aren't like revenues. This is what Forbes has valued the companies at, and the companies being each team. The NFL, right? Its top 3 teams have quite a bit higher valuation than the other three leagues. It looks like Major League Baseball and NBA, at least at the top, are comparable. Now the averages, who knows? Maybe I've got really skewed distributions here, right? Maybe it's that the top three teams in NFL are way above the other, 29 or 32 teams in NFL. So other 29 teams. So we have to do a little more investigation if we really wanted to start to make statements like that. But just based off of the top three teams, it looks like the NFL kind of is the highest demand of these four sports, and NHL kind of being lowest. Okay. Now, one thing that's kind of interesting, just look at the progression. I have been trying to gather this and put these together the last few years. So 2017, you'll kind of notice, I mean, inflation is part of this, but every league has kind of seen an increase. 2019, the valuations kind of continue to get higher and higher. Although you'll notice the NHL changes aren't near as large as the changes to the top three teams and the other three. So what, 4.8 went to 5.5, while 1.5 only went to 1.65. And the same kind of plays out in the average as well. They're all growing. It's just that the NFL is growing, and we'll end up seeing the NBA is growing at a much faster rate than the other two leagues, right? So from 2016 to 17, then in 2019, right, we're kind of seeing these leagues pulled even further away from NHL. And then I skipped 2020 because it was kind of a goofy year to gather data on. But if you look at the most recent, because of COVID, so if you look at the most recent valuations, I mean, the NFL has just continued to increase quite a bit. Kind of notice NBA is really overtaking Major League Baseball. And, the NHL has seen some pretty significant increases in the last couple of years, which has, been, I don't know what to contribute that to, other than just stating that that's the current trend, right? If you want a complete list, and this was, I put 2020 here. I believe the NFL and the NBA valuations are 2021. And I say 2020, it was the 2020-21 season for Major League Baseball. But I think this should be coming out soon. So they should be updating this list relatively soon. But these links, you can kind of see all the teams in every league. Okay. So I then put this file up on Canvas as well. So sometimes I'll show you some data in class. Anytime I do, I'll always put the file up on Canvas. So if you're interested, you can go take a deeper look. We might use it for some assignments kind of moving in the future. We might use some of the data sets that we look at in class for different homework assignments, which I will get the first homework assignment posted up after class on Thursday. So we haven't, we've basically been doing reviews. So there's not a whole lot that I could ask questions on. But after Thursday, I'll get that first homework assignment up there. And you won't be able to work through the entire thing, but the first question or two, you should be able to start kind of taking a look at and kind of working through. So this is, I just copy and pasted all the Forbes data. I also added in some wins to Major League Baseball so I could create those graphs that I was showing you earlier. And you could do the same for the NFL, NHL, and NBA. I just didn't do that because I wasn't going to show you anything from it. But it gives you kind of the current value, kind of the percent change in the valuation of the team, debt to value ratio, revenues, which I believe these are in millions. You'll notice kind of the valuation is in billions because valuation kind of isn't just the next current year. It's just the value of the team. So this is theoretically often to kind of infinity, right? Or at least to the near. There's no near kind of window that will be closing on the valuation. And then they have operating income as well. So we kind of noticed the NFL. I also counted the number of teams that experience losses. So this is really interesting because I have some old data from, I think, 2017, and I have the slides that will kind of state what they were. But, why might I be seeing 20 of the teams experiencing what we would kind of operating income as negative? So we would kind of say they're kind of operating at a loss in this current past year. I mean, a lot of the implications of COVID, right? We've seen a decrease in the number of tickets. Primarily, ticket revenue is what's driving this, right? So that's why the valuations are still increasing because they don't expect that to continue, for the next 40 years, right? And then we've got, what was the other? Something interesting but kind of noticed the one thing that's really interesting. What league didn't really experience this was the NBA. So they still only have 2 teams that actually had negative operating income in the previous year. So, they've been able to kind of withstand the COVID storm a little bit better than the other leagues. I think Major League Baseball, every team experienced a loss, and that's because they really depend on their ticket revenue, right? You think about why would Major League and this is things I don't expect you to kind of memorize this, but we're just talking through doing some critical thinking. Why might the NFL be less impacted by ticket revenue losses or kind of the reduction in the number of people who can attend games than Major League Baseball would be? So even if let's assume for a second, both of them can only sell 50% capacity.
MLB plays more games.
Right? 50% capacity times 16 versus 162 games, right? So a much larger percent of Major League Baseball revenue is going to be coming from ticket revenue, right? So, it's not surprising here that we see every Major League Baseball team had a really rough year, right? So I guess here we might want to start ranking who had the lowest losses, right? But it's kind of interesting data to take a look at. Like I said, we'll use it here and there. But just a kind of quick comparison. This is all 2021 data. It's kind of interesting to look across the different leagues. You can also just see the revenue. So this is in the hundreds of millions. Well, as we look at the NFL, I mean, we're, every team is over 100 million, right? They're in the 3. So you can really see the demand differences here kind of play out, right? And then NHL, almost every team is below 100 million. And then this team was missing data, right? The new expansion team in the NHL didn't have reported amounts yet. Okay. So I'll try to show you things like that throughout the semester, show you the actual data. And next class, we'll hammer more on the theory behind kind of what's the optimal number of wins to choose given the revenues and the expenses that a team faces. Okay. One other thing I wanted to mention here, was, and we'll do 2019. What do you notice about kind of the top teams? And we'll exclude Canada for a second, although they kind of play a role in this. At least in the NFL, Major League Baseball, NBA, what's kind of consistent with the teams that have the highest valuations in each league? Biggest market, right? So if you look here, I mean, New York, Boston is in common, LA, Golden State, it's a little bit of an exception there, but they're also a pretty large market. Dallas, another really large market. And there's other things that play a role as well, right? So Dallas is not the largest market if we think about the city of Dallas, but this is where, metro populations are a good measure of market size. But why might Dallas, even though they're not the largest metro area, have the highest?
Talent.
Quality year to year will matter. But even if every team, right, has these ebbs and flows, so let's say Dallas doesn't have a good year, they'd still look, we can go back. Dallas did not have a good team every single one of these years, but they're always at top. So why? Their fan base is not as dependent on Dallas, the city, right? It is a more national fan base because of maybe previous success, right? Golden State, I would argue probably in the last 5 years, kind of a current thing. They don't solely depend on kind of their metro, or maybe they have a player that brings in people kind of nationally. And so we will use things like metro areas or even average income times population to get a measure of demand, right? Or what's a large versus a small market. But there's some teams that are going to be exceptions to that rule. And for that, we might want to look at something like not just population, but maybe a good indicator of who has a larger market would be something like, I don't know, number of jerseys sold, jersey sales, something that's a more kind of national measure, right? But for the most part, it's highly correlated, right? Valuations and revenue streams are highly correlated with kind of market size. So if we take a look back at that Excel document, and I'll blow it up so you can see it just a little bit better. If we take the NFL, for instance, if we don't look at kind of Dallas, Boston, New York, LA, right? These are all kind of having the highest revenue streams. And as we go down towards the bottom, we've got cities like Buffalo, Cincinnati, Detroit, Cleveland, smaller kind of markets. So it's not perfect, but it's a pretty strong correlation. If we were to run our linear regression, on revenues. And if I had like metro populations, size, which we'll do that eventually, we would see that, that slope coefficient is pretty significantly different from zero, and it's positive, right? That as a team is located in a larger kind of metro population town or city, we tend to see their revenue is higher. Right? All right, so next class, like I said, we'll dive into a little bit more about win maximization versus profit maximization. I'll put up that first, or actually second, since I did the kind of, I just kind of quizzed you over yourself last week. But I'll put up an online quiz after class today, which needs to be done, completed before we start class on Thursday. And I'll also, those 2 readings, I said I'd mention at the end what I want you to do with those. So before you leave, those are under the course readings folder. So beer sales and attendance, and then beer sales and NCAA football revenue. So this is how I want you to kind of just look at these papers. This is all I really expected you, if this loads. So every paper that I'll put up here typically has an abstract. It's kind of a nice, concise summary. If you don't understand everything in the abstract, that's fine. But kind of take a look at the abstract, maybe read a little bit of the introduction, and then I would go down here, wherever it's at, and look at the conclusion, right? And I'm not saying you have to have, come into class like with anything memorized, but just have a general idea of what the paper's questions were, what their findings were, and then we'll start to break it down a little bit more in detail in terms of what their regression equation was, look at some of the tables, some of the regression output that they found, and we'll start to hopefully get pretty good at analyzing these papers and being able to determine what, how they came up with the conclusions that they did. But for now, this first week and probably next week, abstract, intro, conclusion, just kind of skim through those, get a general idea of what the question was and what their findings were. Okay. All right. I'll see you guys on Thursday.